Hi, so my name is Kyle, and I'll be presenting my ITSC 2020 paper, Validation of Image-Based Neural Network Controllers Through Adaptive Stress Testing, which is some work that I did with my advisor, Michael Kokendorfer, as a part of the Stanford Intelligent Systems Laboratory. So in general, this work is going to consider image-based neural network controllers, which is depicted here in this diagram, which you might have some plant, which is the vehicle or robot that you're trying to control. There is some onboard camera sensor, which is recording images, and then you would have a neural network that is trained to take those images and give some predictions. So that could be your control signal directly, or it could be some features that would then be routed through a controller to create some control signal. And so that would be fed back into your vehicle, and this would be running at some frequency in order to control your vehicle using this neural network. So I'll be considering an example application throughout this talk, which is a taxiing aircraft simulated in X-Plane 11. The idea is that we have this trained neural network that predicts the aircraft's position and heading direction on this taxiway just using the camera images. So this is all in simulation, and so the bottom right image shows what the camera would see that's simulated to be on the right wing of this aircraft. So the control law looks something like this, where we have the image from the simulator. We have a downsampling process, which I'm not going to describe in a lot of detail here, but there's more details about this in the paper. But the idea is that this downsampled image allows us to shrink the input that we give to the neural network so we can train a really small neural network. In this case, this neural network has 32 ReLU activations spread over 3 different hidden layers. So it's a really small neural network. And we have it trained through supervised learning in order to give cross-check error and heading error estimates. And that is the position on the taxiway as well as the heading direction on the taxiway. And so we came up with this simple proportional control law, which is the output is the rudder or nose wheel command. And so in this talk will really just be focused on given this downsampled image, what would the rudder output be? But in reality, there's an intermediate step that of predicting these cross-track and heading error positions. And this rudder command is what steers the aircraft. So a positive rudder command would steer the aircraft more towards the left, and the negative one would make the aircraft turn more towards the right. And so this is at a frequency of once per second. And so we can simulate this, and we'll see that we get pretty good results. So whether it's clear conditions or overcast conditions, and no matter where we start on this taxiway, very quickly the neural network is able to control the aircraft back towards the center of the taxiway and then orient the aircraft so that it's falling in the direction that we desire. So all of this, it seems to perform really well empirically, but of course with any neural networks, there's questions about how we've seen everything in testing, or are we susceptible to noises that we would see in real life. So the question is, can image noise cause the aircraft to leave the taxiway? And so typically, when you would have these image-based neural networks, we would consider questions about local robustness or adversarial robustness. But we're going to be looking one step further to see how does this local robustness affect the system over multiple time steps. So first, let's talk a little bit about adversarial robustness. So there's a variety of tools that could be used to solve adversarial robustness queries, but we'll be using Marabou. The idea is that you have this input image that nominally produces some output, in this case the rudder control. And we want to find the input disturbance that could cause the neural network to change its output by as much as possible. So in this case, we're considering pixel-wise disturbances bounded by this value of delta. And we would be saying, is there an image within this delta region that the rudder command changes by as much as epsilon1, for example. And so this Marabou is its out solver, so it's either going to say, yes, there is some image, or no, none exists. And so we can do this search in parallel, knowing that epsilon of 0.0 is trivially sat because that is just corresponds to the input image itself. And we can also say that for some large epsilon value, we know it to be unset, and that's just using expert knowledge. So we run Marabou in parallel by saying, for example, 4 different Marabou queries at different epsilon values. and each one of these is going to return sat or unsat. We can repeat this process, refining that boundary until we find that exact value of epsilon that is where the neural network output is changed as much as possible for some delta level. So we could simulate with this X-Plane 11 simulator what those disturbed images do to the neural network and to the aircraft over time. So this is running X-Plane 11, and we're pausing every few seconds to allow Marabou to compute that worst case perturbed image, in this case the image that pushes us to the left as much as possible, with the maximum change to each pixel of 3%. So we can speed this up a little bit, and we'll find that we're not able to find a sequence of these left sense disturbances that leads us to a failure. We get stuck around 7 to 7.5 meters of cross-track error. We could repeat this for the right sense disturbances, and we would get the same type of result. We're not able to leave the taxiway. So this might give the impression that we're going to be safe with 3% errors, but that might not be the case because we haven't considered all different combinations or sequences of left or right sense errors. So that brings us to the adaptive stress testing algorithm, which is originally proposed by Richie Lee, and is just a way to formulate reinforcement learning with a black box simulator in the loop. And in this case, my modifications to this is to make the action space be the disturbance levels delta either a left sense disturbance or a right sense disturbance. So the smallest action space would just be, say, let delta be a constant value, and have either a left action or a right action, so it'd be 2 actions. But we're going to be using Marabou in order to find the worst case image disturbance. So we're compressing this action search space from this really high dimensional search into just an action space of 2. And then the rewards with adaptive stress testing are 2 parts. There's rewards for finding or getting near failure states. In this case, that would be leaving the taxiway. Or there's penalties for taking less likely actions. In that case, this would be higher delta value, so that's less likely disturbances that you would see for the image. And so we're using this adaptive stress testing approach. We're looking for sequences of these actions that are the most likely to lead to failure. And so we could use a variety of reinforcement learning algorithms. In this work, we use Monte Carlo tree search and deep Q networks, but I'll start by describing the AST algorithm with Monte Carlo tree search. So I'll explain how this algorithm works by using a demo. So we begin Monte Carlo tree search with some initial state, that's our root node, and which is in this case just some aircraft configuration where we're on the center of the taxiway and heading in the right direction. And so as we run this algorithm, we would select an action, either a right or left sense action at some disturbance level. We'd use Marabou to compute what that worst case disturbance is and simulate the aircraft forward 1 second. Now, normally with Monte Carlo tree search, you do these rollouts to evaluate what that new state should be. But because we're using this visual simulator that's really hard to speed up, faster than real world time, we pre-compute a bunch of rollouts from different locations on this taxiway. And then when we need to evaluate a new state, we can just interpolate using this cached rollouts. So this helps us to be 2 to 3 times faster than if we were to try to do these rollouts online. So the idea is that we are building this search tree as shown in the bottom left, where the red nodes are the nodes that we've explored, and the blue ones are the ones that are the best nodes seen so far. So we're more likely to expand that side of the search tree, but Monte Carlo tree search has that classic balance of exploration versus exploitation, so we're going to explore other areas of search tree as well. But this will continue for some number of iterations, but we'll just skip ahead to see what the final search trees look like. The result of running adaptive stress testing would give us these trees here, where the red nodes show the search tree, all the different states that we've explored, and the blue is the policy, the sequence of the disturbances that leads us to the failure. So we can see that for a delta of 2%, we're not able to find a failure at all, which is giving support that 2% disturbances is not strong enough in order for us to leave the taxiway. But for 4%, it's very easy because it's such a large disturbance that we can just go left every time and we're going to leave the taxiway. But it's really interesting for that middle ground where it's 3 to 3.5%, which is where adaptive stress testing finds really interesting ways for the neural network to cause a failure. So we'll take a little bit closer look at this adaptive stress testing solution for when delta is 3%. And the number I want to keep a look at is this rudder error, which is our epsilon value that we mentioned earlier. So if we simulate what that policy was when we found it, we'll see that it's heading towards the right, and it's finding rudder disturbances around 0.1 magnitude, or 0.07, so they're not very strong. But as we get closer to the center line and start turning back to the left, we find some images where the disturbance gets really large, almost 0.2. So these are images where the center line is missing from the image, and so there's not a lot of features within that downsampled image that help guide the neural network and give it a more accurate estimate. So those are the types of areas where the neural network is able to be fooled more easily and is more vulnerable to attacks from adversarial images. So we can expand the action space of adaptive stress testing to allow us to find trajectories that have different delta levels within the same trajectories. So we don't have to just fix it to one value for the entire Monte Carlo tree search. And so we could do 4 actions or 6 actions, in which case we'd have more smaller delta levels. And what we find is that when we expand that action space, we find ways to make the aircraft fail that take longer to reach the failure, but the average delta disturbance used is smaller. So it's able to use the smaller disturbances and only use the larger disturbances when necessary in order to reach that failure. We can also implement AST with a different reinforcement learning algorithm, deep Q networks. The difference is that instead of storing these state action values in a tree, you would have a function that maps your state values to your action scores. So there are some benefits with this approach in that we can incorporate different initial conditions more easily, and the neural network helps to generalize to new states better, and so this can help to improve learning because we don't have this factored into this tree. But there are some downsides, is that it can require a lot of samples to optimize the network, and it can converge to a local optima, so we have to be very careful about how we tune some of these parameters. And it can have trouble learning with rewards of different magnitudes. So we have a really large reward for reaching a failure state and some smaller penalties for taking less likely actions. And because we have a reward function that has very different magnitudes for these rewards, sometimes deep Q networks can struggle since it's doing this approximate representation. Instead of Marabou, we could also just sample 5,000 random images and use the worst case disturbance of those sampled images. And we chose 5,000 because that takes about the same time as running Marabou. But what we find is whether we use Monte Carlo tree search or deep Q networks-based adaptive stress testing, we don't find any interesting failure sequences, and in fact, we can only get to about 5 meters of cross-track error. So this indicates that Marabou is really important in order to find those hard to find images that could cause us to fail. To conclude, we presented this adaptive stress testing method which can find the most likely sequence of image disturbances that leads to failure. We did this by combining the Marabou neural network verification tool with this idea of using reinforcement learning called adaptive stress testing to find ways in which image disturbances can cause failures. And this can uncover something interesting about the neural network. So in this aircraft taxi example, we found that the network was particularly vulnerable when there was a gap in the center line. And so this can help tell the engineers where we need to make the system more robust, or we can build confidence and validate that the system requires unreasonable levels of disturbances in order to fail. So there's lots of room for future work. We could consider continuous action reinforcement learning methods as opposed to just assuming discrete delta levels. We could consider other types of image errors beyond just this L-infinity norm or pixel-wise disturbances. We can incorporate different neural network verification methods besides Marabou to see if we can find something that works faster or is able to scale to larger neural networks. And we could use the results of this method in order to improve the robustness of the neural network, for example, trying to make the network more robust for the centerline gap cases. So thank you for listening.